Hello, this is Dr. Mohammed, and this is another video under the series of analysis of statically indeterminate structures. And today we are going to talk about the moment distribution method. And today we are going to focus on the continuous beam. There are two videos regarding continuous beam, so this is why I put it continuous beam 1, and there is another video that is going to elaborate more on the details of continuous beam, especially for settlement of supports. Okay, now let's go to the some important issues regarding the continuous beam. I'm going to start first with what we call it practical application of the moment distribution process. Actually, in this process or in this practical application, we are going to give some hints about making it faster and quicker for the analysis using the moment distribution in general. So I'm going to talk or give some hints, and after that I'm going to explain using an example. So we can start with this, that from the practical viewpoint, it is usually more convenient to use an alternative approach in which all the joints of the structure that are free to rotate are balanced simultaneously in the same step. Let's understand it clearly here. Actually, before, when we were talking before in the previous examples, we said that whenever we have some points free to rotate, so we have points here like B and C here, so we said that we are trying in every time in the moment distribution, we make balance at each point independently, separately. So we finish the balance here, then we go to point C and make another balance here and carry over, and then go back to B, and so on and so forth. We found actually this is not practical. It takes time because we need to alternate between B and C, making balance here, finish it, and then go here, making balance, and then finish it, and then make the carry over, and so on and so forth. So is there a way for us to balance the 2 points together in the same time, simultaneously? The answer is yes. That we are going to treat the joints of the structure that are free to rotate, they are going to be balanced simultaneously in the same step. Okay, so that's the main important understanding for the first hint here that we are talking about, which is, this is what we call it the practical implementation of the moment distribution method. And in the same time, how we are going to make the carryover. So this is related to the balance. Okay, balancing. We are going to balance all the free joints to rotate. We are going to balance them together. So what about the carryover? All the carryover moments that are induced at the far ends of the members are then computed simultaneously. So it is in the same time also. Okay, at the far ends, the members are then computed simultaneously in the following step. Okay, and so the next step after balancing, we are going to make carryover. Okay, for the far ends, and the process of balancing the joints and carrying over moments is repeated until the unbalanced moments at the joints are negligibly small, as we have done before in the previous examples. Okay, so now this is an important issue. What I want you to remember here, the two steps here, or the two hints here. The first hint, that we are going to make the balance simultaneously, and then in the next step we are going to make carryover simultaneously, computing the carryover simultaneously for the far ends, and then we are going to make the process of balancing and carry over moments is going to be repeated until we encounter a negligible small moment at the end to be balanced. Okay, I hope that you can understand these two steps and keep them in your mind, because we are going to use them in our example. Okay, now let's have an example to understand what we are talking about. Assume that we have this example, this span. Actually, this span already we have we have worked it out before in the previous video using the the common and classical way, which is balancing B, then balancing C, and then go back and forth and so on. But now we are going to balance both points together. So as a reminder, this is the span of our beam. We have fixed support at A, we have fixed support at D, we have 2 points B and C which are having rollers, and as we have explained in the previous video, point B is free to rotate and point C is free to rotate. Then we are going to make the distribution factors at point B and point C only. Okay, and then we are going to use our method, the new method, the practical method, for balancing and carrying over, and then we're going to end up. Let's see what and how we can start with this. As you can see, the span here loaded with distributed load on AB, concentrated load on beam BC or span BC. The spans are 20 feet, and this concentrated load at the middle of point or the span BC. The first thing is the distribution factor, and I think that we have explained it before. So in the previous video, if you go, you are going to find the details of how we can obtain this distribution factor. Seemingly we have EI on the right and left of point B to be the same. We said that EI it is constant for all. Then we are going to have the balance to the distribution factor to be I over L, because the far end is fixed here and here also. So I over L over all the relative stiffnesses framing into this point. So it is going to be over 2I over L. So we are going to have 0.5 here and 0.5 here from the left and from the right. In a similar fashion, we are going to do this for point C, and we're going to find that because we have like this span is 20, this span is 15, then you're going to find the distribution factor is not 50-50, it is going to be around 0.4 here and 0.57 here. Notice that whenever that we have the span with less length, it has what? Higher distribution factor. And the span with more length, it is going to take less distribution factor. Okay, so keep this in your mind. Okay, of course, if we are talking about the same inertia, which is our case, we are talking about the same inertia for the beams. Then the first step is to get the fixed end moments. We already have explained it and obtained it in detail in the previous video. So we have it here, 50 and minus 50, 75 and minus 75. Okay, now let's go to the practical implementation, as we have said. The point is, we are not going to look to be moments, unbalanced moments. We're not going to balance them individually, but we are going to balance them in the same time we're going to balance C. So for example, 75 minus 50, it is 25, the unbalanced moment. This 25 positive sign is going to be given 50-50 here and here. So the 25 is going to be with the negative sign 12.5 negative and minus 12.5 negative, okay, at the right and left of point B. Okay, this is the balancing moment, and now they are balanced. This is balance. In the same time, in the same step, we are going to balance the joint C. So we have only minus 75 here because this is the fixed end moments. We do not have anything here because we do not have any loading, so there is no fixed end moments here. Only we have minus 75. This needs to be balanced by these distribution factors. So we're going to multiply 75 by 0.429 and it gives us plus 32.2. Take care of the sign. It is negative. When we make the balancing moment, it is negative opposite sign. So 32.2 here and 42.8 here. So this is in the same step. Then you are going to draw this line here, this line. I indicate this line to indicate that all the joints are now balanced. Because now at point C, if you calculate these three moments, in this we call this is the loop, or this is one cycle or one cell, you're going to find that their summation is 0 because it's balanced point. And if you calculate the summation of these 4 moments for point B inside the cycle or inside the cell, you're going to find that they are 0. This means that they are balanced. So the first or the second step is balancing the joints simultaneously. The moment distribution process is started by balancing joint B and C together in the same time. Okay, so now we finished the first cycle. Now let's go to the second cycle. What we are going to do, carry over for all the moments. Okay, so we are going to look to this point. Let's erase everything here, Shift E, and now we have this minus 12.5. We want to make carryover. The far end here is what? Is fixed, so the carryover should be half. That's right, half of the moment. Minus 12.5, it will be minus 6.3. As we said many times, carryover should maintain the same sign. Okay. Similar way, this minus 12.5, far end here, it is fixed also. So half of this minus 12.5 will be given here, which is minus 6.3. Okay. Now we have this is already given from the carryover. 32.2, half would be here because the far end here is fixed, as we mentioned before. So now we have, this is the carryover moment. We do not have anything here, right? We do not have anything here because there is no moment here. But we have this 42.8 carryover far end. As you can see, it is fixed. So we have 21.4 here. So now these are the carryover moments. Now we need to balance these carryover moments. So we're going to make the cycle here or the cell. Simultaneously, we are going to look to the 16.1 at point B, and we are going to distribute it using the distribution factor 0.5 and 0.5, half and half on the right and left. Take care, as I said, positive sign, negative and negative here. Similarly, this minus 6.3, it is going to be balanced. So we're going to put plus 3.6 and plus 2.7 right and left based on the distribution factors here. So we are going to draw a line here. This means that this cycle ended or this cell ended because all the moments here, they are having 0. This means that balanced point C, B, and balanced point C also. Now draw this line and you are free now to make the next cycle or the next repetition of the carryover. Make the carryover here, minus 8.1 for in fixed, half of the value, and minus 8.1, half of the value here, 2.7, half, 1.4, 3.6, half of it, it is 1.8. Then take care, it is with the negative, sorry, it is the same sign. Then this is unbalanced moment. Then you are going to make a round of balancing. 1.4, half of it here, half of it here, because of the distribution factors. 4.1 negative, so it will be positive 1.8, 2.3 based on the distribution factors here. And then draw the line. This is balanced point, and this is balanced point here. Then make the carryover. So 2.3 is going to give us 1.2 here. And this 0.7 minus is going to give us minus 0.4, and this 1.8 gives us plus 0.9, and this minus 0.7 is giving us minus 0.4, half of it, with rounding off. Then we need to make another round of balancing, 0.9. You can feel that the numbers are going smaller and smaller. This means that the unbalanced moment is going smaller. So 0.9, half of it here, half of it here, 0.4, distributed here and here, and then we're going to have another round of carryover moment, 0.1 here, minus 0.3, 0.1 and minus 0.3. Seemingly it is going to be very small moments. After that we can stop at this cycle here. This is the last carryover. We're going to make one round of balancing, which is, as you can see here, 50-50 here and here, 0.1 and 0.2 based on the distribution factors. And then we draw the line. This is the end step for us. what we are going to do, as usual, we are going to sum up algebraically all the moments that is being carried over here on point A. Found it 38.9, and at point B we're going to sum up all of them. They're going to be minus 71.8. Then check it up with summing on the right. It should be with the same magnitude but different sign. Similar at point C, we're going to sum up and we'll find that same magnitude, different sign. And then at point D, sum them up. You are going to end up with this value. Okay? So we have this value. These are the end moments now. Okay? This is what we call it the end moments. Okay? These are the end moments, and we can draw our structure now. Okay? So this is clearly explains to us what is the meaning of what I was talking about, which is the practical point of view, looking to balancing in the same time simultaneously and working on the carryover simultaneously and repetition until we got negligible small moments. Okay, this example is very clear for us now, and we can implement this practical implementation of the moment distribution method for continuous beams. Okay, now let's go to another point, which is analysis of continuous beams with some hints related to it that is going to make it easier for us. First of all, we want to systemize or to make it a system for us, or to put some steps for the procedure so that you can go through these steps directly to solve any continuous beam problem using the moment distribution. First of all, we are going to calculate the distribution factors as we have seen in the previous video. And then we are going to compute fixed end moments, second step from the front or the back cover of the textbook. And after that, balance the moments at all, take care of this word, all the joints that are free to rotate. As you know, we are balancing the points that are free to rotate. And number 4, determine the final member end moments by summing all members end moments. So we are going to determine the final member end moments by summing all the members end moments, as we have done here before. We were summing all the moments here, then it gives us the final end moment. Okay, and then we are going to compute the member end shears by considering equilibrium of the members. Actually, when we are having the end moments, if we assume that something like this, then we need to get the shear. So we are going to take the moment here, for example, and then we are going to find that we need to obtain the shear here. So equilibrium of the free body diagram of the span would provide us with the shears, okay, by considering equilibrium. And the final step is determine the support reaction. After having the shear of the span from two sides, for example, we're going to have this shear from two sides. The summation, algebraic summation, is going to provide us with the reaction at each point by considering the equilibrium of the joints. Okay. Okay, so the reactions are going to be obtained by the equilibrium of the joints, while that the shears are obtained by considering the equilibrium of the members. Okay, that's the hint. This is considered to be the main 6 steps that you need to take into consideration when you are solving the problem using the moment distribution method. Well, we are ready now to go to examples, but before going into the examples, we are going to highlight something that is important for us related to the beams with simple support at the end. So whenever that we have like simple support at the end, okay, if we have something like this, if the end is simply supported, then we are going to make it easy for us. We're going to make it easy for us. We're going to use the relative stiffness for this span. So we're going to say that the relative stiffness for this span is going to be 3EI over L. Do you remember this? I have explained it like 2 videos before. The relative stiffness, if the far end is Okay, if the far end is fixed, then we are going to say that here this relative stiffness for the far end here, it is going to be 3 over 4 I over L. Okay, then we're going to use this. So the analysis of such structures can be considerably simplified by using the reduced relative bending stiffness. We call it the relative bending stiffness, which is K equal to 3I over 4L, which is 3 over 4 IL, 3/4 of IL. Okay, for spans adjacent to the simple end support. So this is the span that we're talking about. So we're going to take the relative bending stiffness for it to be 3 over 4 I over L. Okay, so this is very nice. We have reduced the stiffness now. Then what should we do? How it will simplify our process? This is going to explain how it will simplify. When using reduced stiffnesses, the joints at the simple end supports are balanced only once during the moment distribution process. That's the key word here. So this point is going to be balanced only one time. No need to balance it every time, okay? Well, I'm going to explain it through the example, but remember that very well, that the far end hinged, or the simply supported end, far end, this would simplify the process by balancing it only once. Okay, we're going to balance it only once during the moment distribution process, after which they are left unclamped as if they are not clamped. Okay, so that no moments can be carried over to them. So also we are not going to give them any moments. Okay, because they are simply supported. You can imagine this. There is no moments here going to be developed, okay, to them, as the interior joints of the structure are balanced. Okay, I think that maybe you didn't understand very well what I have said here, because this is only sentences. I want you to understand from them two things: that we are going to use relative bending stiffnesses for spans ending with simple support, and we are going to balance them only once during the moment distribution process, and there is no carryover for them. This is what I want you to remember from here. So let's have an example to understand what I've said. Maybe in the next time we're going to have another example that is showing what I have meant by these 2 points. But anyway, we're going to understand using this example, simple example, to apply the moment distribution on the continuous beams. So we want to determine the member end moments for the 2-span continuous beam shown by using the moment distribution method. As you can see, we have a fixed support at point A and fixed support at point C. We have distributed load on the span BC and concentrated load at span AB, and the spans, as you can see it here, we have EI to be constant. For this case, it will be simplify the method for us. It would simplify the method for us. Okay, now let's go to the next, which is let's obtain the moment distribution, the distribution factors here. So we have at point, first of all, how many joints that is free to rotate in our case. If you look here, actually we have point A to be fixed, we have point C to be fixed, only point B that is going to be free to rotate, right? So we are going to make the distribution factor, or calculate the distribution factor at this point, because this is fixed and this is fixed, so it is going to be easy for us. We're not going to make the balancing and so on for point C or point A, only we're going to make it for point B, balancing for the free points only. Okay, now let's assume that we want to get the distribution factor on the right and left of point B. How we can obtain it? Look to span BA, far end is fixed, and span BC, far end is fixed. So the denominator of the distribution factor for BA is going to be KBA plus KBC. Far end is fixed, in both cases. So we are talking about I over 25 here and I over 30 here, which is I over 25, I over 30. And the numerator is going to be BA, which is this BA, far end is fixed, as we have said. It is going to be I over 25. The distribution factor is going to be 0.545. For the case of BC, it is almost similar, the same as here, except that we are going to use, yes, I over 3, because the span of BC, it is 30 foot, not 25. So now we are going to use the same equation here, but we put 30 instead of 25 and get the results. So we're going to have it 0.455. So we are going to put them here as we have obtained them. This is the distribution factors. What are the roles of the distribution factors? They are distributing the unbalanced moment to the right and left of the joint. Okay, now let's go to the next step. So now this is maybe the first step for us, the distribution factors. The next step is what? Exactly, the fixed end moments. We want to calculate the fixed end moments. So here at point B, we need to know what is the fixed end moments that is going to be developed here, and also BC and CB. So we have AB and BA. So we have fixed end moments AB and BA, which is related to span AB. And then for span BC, we have two moments, which is two moments here, right? Fixed end moments, which is BC and CB. So we have BC here and CB, right? Okay, so for span AB, we have the fixed end moments is going to be calculated easy for us. For a span with a concentrated load, not in the middle, take care. From the back cover of the textbook, you can find the value of the fixed end moments at point A, which is fixed end moments AB. It is going to be the load times the shorter span times the longer span to the power 2 and over the total span to the power 2. That's for AB. And take care, this moment is counterclockwise, so it is exactly positive here. So it is counterclockwise. Okay, as you can see here, counterclockwise. So it is positive. Without thinking, we are going to put BA the same magnitude, which is 64.8, but the sign is going to be negative. So we put the sign to be negative here because it is clockwise fixed end moments. So the fixed end moments for BA, it is going to be minus, I'm very sorry, because the magnitude is going to be different, because it is the force, the concentrated load, not in the middle. So I was confused. This is not in the middle, so we are going to have different spans here. So I'm very sorry, they are not going to be the same in magnitude, but of course we are going to have the negative sign. But in order to get the value or the magnitude of the moment here, which is fixed end moments, and BA is going to be 18 times 10 to the power 2. Okay, this is the shorter span here because we are talking about this moment. So we're taking about the other span, the shorter span, times 15 over 25 to the power 2. Then we are having this magnitude, which is 43.2, and it is negative because it is clockwise. Okay, now let's go to the other span, which is BC and CB. So we have here fixed end moments. This is fixed end moment, which is going to be BC, and here this is fixed end moment, which is going to be CB. As you can see, it is distributed load, so it is easy. It is WL squared over 12. This is the fixed end moments. This one is going to be positive because it is counterclockwise, and this moment, which is CB, it is going to be negative because it is clockwise. So we can calculate it easy. FBC, it is 2 times 30 to the power 2 over 12 gives us 150, and it is positive because it is counterclockwise. So we are going to have it positive. And blindly you can go it and put it here negative with the same magnitude for CB. as we said, they are the same. Okay, so now we have the fixed end moments, and we are going to put all the values that we have obtained here using the same signs. We're going to put it here as as we have obtained them. Okay, 150 here and minus 150 here. So this is the first step for us. This is the first step for us. Okay, now let's go to the next step. So in the next step we are going to make exactly balancing the point. The point that needs to be balanced is going to be B only. As we said, A is not free to rotate, C is not free to rotate, B it is free to rotate. So we are going to make the balancing at this point only, B. Okay? Okay, we know the distribution factors. We know all the fixed end moments. So look to the fixed end moments. We have minus 43.2 plus 150. So it seems that we are having unbalanced moment. By summing them up, we're going to find that the unbalanced moment at point B is going to be positive 106. This 106.8 is going to be distributed to the right and left based on the distribution factor. So we have 0.54 here times 106. It is going to give us minus 58 here. So 0.54 distribution factor times minus 106, it gives us minus 58.2. Okay, minus 58.2. Take care of the sign. Here we put it minus, because whenever that we are making the balance, we should always take the opposite sign. We should take the opposite sign. So now this is minus 58.2, and on the right it is going to be the remaining part, which is 0.455 times 106, 0.455 times 106.8 with the opposite sign, so it is negative here. So it gives us minus 48.6. Okay, this is the balancing. So draw the line here. Now these are the balancing of this moments. If you calculate and algebraically sum them up, you are going to find that they give you exactly 0. They are going to give you 0. Okay? Okay. Now let's go to the next. The next is the carryover moments. We are going to make carryover. So this moment at point B is going to carry over, give some moments here, half, because the far end here is what? Fixed. So half of it will be given here with the same sign. And here minus 48.6, half of it will be given to the far end, which is fixed here. Okay, so it is half of it, which is minus 24.3. So this is the carryover. Okay, this is the carryover. After multiplying this by half, it gives us minus 29, and this is, after multiplying by half, it gives us minus 24.3. And then we're going to end up with this, that joint B is the only joint, as we said, in the structure that is free to rotate. And because it has been balanced, look here, it has been balanced. This is 0. It is balanced now. After making the carryover, there is nothing here. It will not take any moment from any other place, right? So this means we have balanced the main point that is free to rotate. This means that we are going to end. We put a double line here. This means that already we can end our moment distribution in 3 steps only. So the final step is going to be the summation of these moments. Again, why we stop here? Because of this. That joint B is the only joint of the structure that is free to rotate, and because it has been balanced, we end the moment distribution process. So we end it here. Then we're going to sum them up for every column, and the values is going to be given underneath every column based on the summation. These moments, we are going to take it and put it in the free body diagram of each span. So we're going to put here, this is the moment here, this is positive, counterclockwise, as you can see here. This is negative, it is clockwise, as you can see here, with the same magnitude. And for the span BC, it is 101 positive, it is counterclockwise. and here at point C it is negative, so it is clockwise 174. Then these shears of the spans, we can obtain them by balancing the member. Okay, taking the moment here, you can obtain the shear here. Taking the moment here, you can obtain the shear here. And then the final reaction can be obtained by summing up the shear at each joint. So here and here, sum them up, it would give you the final support reaction. Okay, final support reaction. Okay, I think that you can understand it very well, and I hope that you can understand the process and how much it is easier for us now. Remember well that we are balancing the same point, and we end the point that is only free to rotate, and if it's balanced, this is our main goal. Now it is balanced, and there is no carryover from other sides, because they are here, as we said, they are fixed. So there is no carryover from them, and based on this, we are ending with our point B to be balanced. That's it. Okay. Okay. Now let's go to another hint, and I want you to know it, and then we're going to have an example for this. Sometimes we encounter structures with cantilever overhangs. Cantilever overhangs. As you can see here, we have fixed at A and distributed load here, and there is point B, point C, and point D is free, and it is overhang here. This is a cantilever with the length A. So whenever that we are talking about this, the fixed end moments that we are going to have for all the spans, we know it is going to be based on the distributed load here in AB and BC, but here at CD, we are going to put the magnitude of the moment due to the distributed load. That's it. So if we are going to cut at point C here, so we are going to deal with this cantilever as if it is a statically determinate portion. Okay, so we're going to say that we have distributed load here, we have a span which is A, then the value of the moment at the end is going to be W A squared over 2. Okay, so that's the point. Okay, now we understand about this. So this W squared over 8 is going to be dealt with as it is like the fixed end moments. So we're going to put it in the next step after the moment distribution. Well, so does this help us in anything? Yes, it will help us. The cantilever portion, CD, does not contribute to the rotational stiffness of joint C. Actually, that's right. It does not contribute to the rotational stiffness. Okay? The distribution factor for its end is 0. We're going to put it, the distribution factor here, distribution factor equal to 0 here. We just put the moment, but its contribution to the stiffness of the point is going to be neglected, or there is no contribution. The moment at NC of the cantilever, which is at this end, which is NC, however, does affect the unbalanced moment. That's right. This is why we are going to take this moment into consideration. But the stiffness of this part is not going to be taken into consideration. Okay, along with the other fixed end moments in the analysis. I think that you didn't understand it very well because it's written sentences. You're going to understand it through the example. Okay, let's jump into an example and see how we can implement what we have learned till now. So we have a beam, as you can see here. Determine the member end moments for the two span continuous beam shown by using the moment distribution method. So we are having the span, and we have like 6 meter here, 9 meter here, and 4 meter overhang or a cantilever with a concentrated load at the tip, and we have like a distributed load between B and C, which is 10 kilonewton per meter. So we are having here, as you can see, like different spans. The first one is fixed. Here it is a roller, here it is a roller, here it is a cantilever. Here it is a cantilever. So we have EI, it is constant for all of them. Okay, now let's go and try to implement what we have learned. First of all is the distribution factor, right? We need to look to the distribution factor at free to rotate points. Okay, so we need to look to the free to rotate points. Point A, it is fixed. Point B, roller here, so it is free to rotate, so we have B. And C, similar, it is free to rotate. D, we're not going to consider it actually here, as you are going to see. We're going not to look to this part at all, just we are going to take its contribution, which is the moment. So 30 times 4, it is going to give us 120, as I'm going to show to you, and put it here and forget all about this part. Okay. So first of all, we know now that we have 2 points that are free to rotate, which is point B and point C. And point B, we are going to calculate its distribution factors. So first of all, here we are going to look to the span as something like this. This is point A, so this is point B, and this is point C. Okay, where is point D? It is as if it is not there. We are going to put a 120 kilonewton, okay, as kind of contribution at this point. So this is point A, this is point B, this is point C. Okay. Now this point is point what? Point C. Its far end is what? Simple. It is hinge. So now we are going to use and simplify our distribution and our moment distribution process. We're going to consider it as far end is hinged, and we are going to use 3 over 4 I over L for this span to be used in our moment distribution. So based on this, the distribution of point at point B, the far end here is fixed, so KBA is going to be I over L. This is the common, right? So KBA, it is going to be I over L, which is 6 here. And KBC, it is going to be 3 over 4 I over L, which is 9. Okay, so it's going to be 3, this is KBC, it is going to be 3 over 4 I over L, which is 9, and equals to I over 12 at the end. Okay, so take care, we have used here the relative stiffness to be 3/4 I over L. So now we consider this to be far end as simple. Okay, and now the distribution factor at point B, DFBA and DFBC, right and left, it is going to be, for BA, it is I over 6, far end is fixed, so I over 6. The denominator is going to be the summation of the two relative stiffnesses, which is I over 6 plus I over 12, which of BC. Okay, so this one is KBA, this one is KBC. This is not I over 12 directly, this is relative stiffness, far end is hinged, so it is 3/4 I over 9. Okay, okay, so now we obtained this distribution factor here, it is 2 over 3, this 2 over 3. Without any calculation, the distribution factor for BC, it must be 1/3, because the summation should be 1. Okay, so now the distribution factor BC, it should be 1/3. Okay, and this is great. Now let's go to the next step, which is exactly the fixed end moment. Now we have, okay, now there is something that maybe I forgot to say here. Regarding this, this CB, here the distribution factor is going to be 1. Okay, the distribution factor is going to be 1. At point C, the distribution factor should be 1. Why? Because we said that it is going to be simply supported. So the distribution factor, any moment that is going to be developed, it should be carried by CB. There is nothing here. As we said, we are going to neglect this part as if it is not here. So we are dealing with CB, and it will take distribution factor as 1. Okay? So again, the philosophy is removing the cantilever, putting its contribution, which is the moment, and using this point as a far end hinge for the span BC. That's it. Okay? Now we have the distribution factors given already or calculated as we have said. Then let's put the fixed end moment. For member AB, there is no loading here. So there is no fixed end moments here and here. Okay? Nothing here and nothing here. Because there is no loading, so there is no fixed end moments. For member BC, it is simple for us. The fixed end moments is going to be WL squared over 12. Right? And 10 kilonewton, then we can obtain it well. So FEM BC, which is here, BC, equal to plus, because here the moment is going to be, as you can see, counterclockwise, so it must be positive. Okay, and 67.5 from where? WL squared over 12. Easy, you are going to find it 67.5. And for CB, fixed end moment CB, it is going to be the same magnitude but different sign because it is clockwise here. And for fixed end moment CD, what is the fixed end moments for CD? It is its contribution from the moment. So what is its contribution here? The contribution is 30 kilonewton times this distance, which is 4 meters. Okay, and then it would give us 120 kilonewton. Okay, 120 kilonewton. Okay, so this is the statically determinate cantilever portion. This is the free body diagram of the cantilever portion, right? So this means that this moment needs to be reflected on the beam at point C. So we will use this amount of moment here. Okay, and this is going to be added at this point at point C from the outside. Take care of the sign. It is positive. It is positive. Why it is positive? Because we are talking about this part, which is CD. So as if that we have like moment here. So take care. This moment is the effect of the cantilever on BC. However, this moment, which is the fixed end moments inside the span CD, it is the moment that is going to be developed here. Okay, so we put it as positive for this reason. So 30 times 4, it is equals to 120. 120. Okay, now let's go to the next level, which is related to the balancing. So now we have 67.5, it is unbalanced, and we have here also minus 67.5 plus 120. This is not balanced moment seemingly at point C and not balanced moment at point B. Simultaneously, we are going to balance them using the distribution factor. So 67.5 with negative sign here, multiply 2 over 3 times 67.5, it gives you 45, and 1 over 3 times 67.5, it gives you 22.5. And as I said, the negative sign applies. And then for this point, we have minus 67.5 plus 120. We are going to find the difference is exactly 52.5, and it is positive. This is the unbalanced moment at point C. All of it is going to be carried by the span BC, so we put it here, minus 52.5. Then draw the line, because this line means that this cycle or this cell is balanced now. So we have balance. This is the balance. The summation is 0 here, and the summation of all of these three moments, they are 0 also. That's it. Now let's go to the carryover. So this moment here, minus 45, carryover, far end is fixed, so half of it will be here with the same sign. And here minus 52.5, okay, it is going to give us half of it here, 26.3. Well, we should, if we are going to talk about this 22.5, it should be carried over here, but we didn't find something here. We didn't carry over. Why? What is the reason? Yes, remember the hint that I said to you. This point, which is point C, we dealt with it as a simple. Okay? So this point, we dealt with it as simple end, or like hinge at the end. We neglected this part, so the far end is simple. So I want to remind you with, yes, here. So the cantilever portion C does not contribute to the rotational stiffness. The distribution factor for its end is what? 0. Okay, that's number 1. We put it as 0. The moment at end C of the cantilever, however, does affect. We said that the moment contribution is going to be effective and dealt with at the fixed end moments. Before this, we mentioned about something related to the, yes, here, beams with simple supports at the ends. We said that when using reduced stiffness, we have used reduced stiffness already. We have used this 3 over 4I over L. The joints at the simple end supports are balanced only once. So we're going to balance it only once. C is going to be balanced only once during the moment distribution process, after which they are left unclamped so that no moments can be carried over to them. There is no carryover moments that is going to go to these ends, to them, as the interior joints of the structure are balanced. So this is what you are going to understand from here. So this means that this moment cannot be carried over here. Why? Because this simple end now, it is point C, it is balanced. So it is balanced only once, one time. So no need to make anything else. Stop here. So do not make any carryover factor. Just you are going to sum them up directly to the end. And here sum them up directly to the end. So now it greatly simplifies the process, or the moment distribution process. Okay, greatly simplifies the process. Okay, now we have the carryover moment here and carryover moment here. Then this minus 26, it is unbalanced at point B. So we are going to distribute them, or distribute it again with the negative opposite sign. So based on 2/3 and 1/3, right and left, and then we're going to find this, draw a line here. This is a balanced point. As you can see, the moments are reducing. Okay, and then in the same time we balance this point, or this joint, which is joint B, and this joint, which is joint C, already balanced from the previous step. So now there is nothing to balance after that. Just we are going to make one carryover to the far end here, half of 17.5, and that's it. Why that's it? Because there is nothing here to be balanced after that. There is no carryover from here. We stopped. There is nothing here. So there is nothing would be carried to this point. And from here, from this side, there is no carryover. There is no carryover. There is no unbalanced moment here to carry it over here. So there is nothing here also. We are going to stop here. Okay. Then sum up all the moments here gives you minus 13.7. Sum all the moments here at point B from the left gives you minus 27.5. For your check, the right of point B should give the same value, the same magnitude with opposite sign. And similarly at point C, from the very first beginning we stopped it because we balanced it only once. So we have minus 120 here and 120 positive here, and they are balanced. Okay. Now put these moments on the free spans, or free body diagram of spans, and you can obtain the moments at the end of the spans, and then the shears as well. Okay. Okay, shears and reactions. I think that this is the end of our video for for today, and I think that now we can understand. Please try to work out this example again by yourself. You're going to understand two things regarding the cantilever end and the simple supported end. And remember that we use the relative stiffness 3/4 I/L for this span, which is having the far end to be as if it is simple, and we are making only one balance step for this point, and there is no carryover would be there for it. And then we're going to balance the other points. If we're going to balance it, we find that it is going to end up very early for us. This is the end of this this video. In the next video, I'm going to talk about some examples for support settlement. Thank you, and see you in the next video.